Section 2.4 and 2.5, Theorems about roots. So here we get to the third part of our three-part series on finding zeros of higher degree polynomials. We started off with our simpler techniques of finding GCF, of using quadratic techniques, quadratic formula, or factoring. We applied grouping, but there was still one more technique that we needed to get to, the rational root theorem. In this lesson, we're finally going to get to the rational root theorem, but it's not going to be until the second half of the lesson. Before we get to that part, we're going to take a step back and kind of turn things around a little bit. We're going to look at these problems Jeopardy style. In other words, we're going to start with the answer and work backwards to figure out what the polynomial was. So the first thing we wanted to be able to do is to write a polynomial given its roots. Once we can do that, we're going to turn it back forwards again, and we're going to go back to finding zeros, but as an intermediate step to the rational root theorem, we're going to start by me giving you the first solution, and then you have to find the remaining solutions. Then we're going to go full force into the rational root theorem. In other words, here is a random polynomial, find the zeros. None of the other techniques work. Let's try the rational root theorem. And we're going to see how these last two standards, once we get to it, these last two learning goals are going to tie in together very closely. So let's start with the easy questions. Write a polynomial with given zeros. So here are some zeros. Here are some solutions to the polynomial. I want you to tell me what the polynomial was that had these solutions. So if you think back to when we originally started solving polynomials, the question was, here's a polynomial, find the solutions. Well, our general technique was to start with the polynomial, factor out the polynomial, set each factor equal to 0, and then solve each factor individually. So if we think about that process backwards, it's just a matter of taking the zeros that we have, turning them into factors, taking those factors, multiplying them together, and then we will have a polynomial that would represent those solutions. So that's what we're going to do. Let's look at the first one. I have x equals 4, -3, and 2. So remember, each one of these came from their own unique factor. So x equals 4 must have come from the factor x minus 4. X equals -3 came from x plus 3, and x equals 2 came from x minus 2, because if I were to take each one of these factors and set them equal to 0, x minus 4 would produce a solution of 4, x plus 3 would produce a solution of -3, and x minus 2 would give me +2. So these are the factors that produce those solutions. So let's just multiply these through to get a polynomial that would produce those solutions. Now, it's multiplication. It doesn't matter what order you multiply in. You could multiply the first two and then the third, or maybe the first and third and then the second, or what have you. I'm just going to multiply from left to right because I don't see any advantage otherwise. So if I FOIL out x minus 4 and x plus 3, I'll start with x times x, which is x squared. Then for my foiling, I do the outside and inside terms. Outside would be x times 3. Inside would be -4 times x. So, and then I would just combine like terms. +3x and -4x gives me -x. And then last, -4 times 3 gives me -12. So multiplying x minus 4 and x plus 3, I get x squared minus x minus 12. We're not done yet. We still have to multiply through the x minus 2, so we're just going to keep multiplying through. We wouldn't call it foiling anymore. Foiling is strictly for a 2x2 multiplication problem. This is a 3x2. So we're just going to distribute one piece at a time. Now, it doesn't matter what order you can do. You could do x squared onto both x and 2, and then x distribute, and then 12 distribute. I like to start with the smaller of the two factors, x and x minus 2. And instead of distributing x squared minus x minus 12 onto x minus 2, I like to think of it the other way around, x minus 2 onto x squared minus x minus 12. So I'll start with x, multiply it times everything inside, and then I'll move on to -2 and multiply it times everything inside. So x times x squared gives me x cubed. X times -x gives me -x squared. X times -12 gives me -12x. I'm done with the x. I'll move on to the -2. -2 times x squared, -2 times -x, -2 times -12. So now combine like terms and I'm done. X squared and -x squared and -2x squared gives me -3x squared. -12x and +2x gives me -10x. Bring down the 24. Voila. So this polynomial, if I were to set it equal to 0 and solve, would produce these solutions. All right, here's another one for you to try. Hit play when you're ready. So this one we can pretty much start off the same way, turn each solution into its own separate factor. So I'd have x minus 0, x minus 1, and x plus 1. But then I realized x minus 0, well, that was a waste of energy to write x minus 0. Anything minus 0 is whatever you started with. Don't write x minus 0, just write x. Remember when we were solving by GCF, when we factored out an x, we inherently would have had x equals 0 as one of our solutions. So if I have x equals 0 as one of my solutions, then I expect to see just a lonely x sitting outside the factorization. Now, once again, I could just multiply from left to right. It really doesn't matter. But I notice x minus 1 and x plus 1, these two are special. These are what are referred to as conjugates. Remember, conjugates are basically binomials where the only difference is you have a positive version and a negative version. It's not completely opposite. You know, this is a positive x and this is still a positive x. It's just the second number that changes sign. So I have positive x plus 1. I have positive x minus 1. And when I multiply this together, I always get the same result in that when I multiply first times first, I get first squared. When I multiply last times last, I get last squared. But when I multiply the outside and inside, when I do x times 1 and negative 1 times x, those outside-inside terms always cancel out. So when we're multiplying conjugates, it's easier just to remember the shortcut. So if you're multiplying a minus b and a plus b, when we multiply those together, FOIL it out, it always turns out to be a squared minus b squared. In other words, the difference of squares. Multiplying conjugates produces difference of squares. Just like if we have difference of squares, we can factor it into conjugates, a plus b, a minus b. So in the future, please don't waste time actually FOILing something like this out. Just go straight to the answer. It's x squared minus 1. Since it's a is in this case is x, b in this case is 1, it doesn't really matter whether you use positive 1 or negative 1 because it's going to end up the same way either way. If I FOIL it out or just go straight to the formula, it's always going to be a squared minus b squared, so x squared minus 1. Now we still have that x on the outside, so let's distribute it through, and we have our polynomial. Now let's address something interesting that comes up when we're solving polynomials. Do you ever notice how when you're solving a polynomial, when you have a problem that requires that you take a square root, you always have the positive and negative version of that square root. If I have x squared equal to 5, I take the square root, I get positive and negative square root of 5. If I have x squared equals negative 5, when I take the square root, I still have a positive negative square root, but because there's a negative underneath, we now have I, because of course I is a square root of negative 1. So because when you are solving, when you have to take a root, you always have to include both positive and negative versions, that kind of tells us something. That tells us that square roots always appear in pairs, a positive and a negative version. And we formalize that in the conjugate pair theorem. And it says if you have a solution that has a radical in it, for example, the binomial a plus root b, or keep in mind that the number I is a square root because it's the square root of negative 1, a plus bi. If you have a plus root b or a plus bi as one of your roots, as one of your solutions, I'm not using the word root here to mean square root, I'm using root to mean solution, then that means it must have come in a pair. Therefore, a minus root b or a minus bi must also be a root. If I give you a problem and I tell you that x equals the square root of, let's say, 15, then I can assume that the negative square root of 15 must also be a solution. Or if I give you 2 plus the square root of 5, I can go ahead and assume that 2 minus the square root of 5 must also be a solution. And for that matter, if I tell you 2 plus 5i is a solution, I can assume that 2 minus 5i must also be a solution. Because, remember, square roots always come in pairs. I have a positive version, I have a negative version, and please keep in mind that the number I is a square root. It is the square root of negative 1. Therefore, any rules that apply to square roots should also apply to the number I. So let's do the same question that we were doing before. We're going to write a polynomial with given zeros, but this time I'm going to give you this, negative 3 and square root of 2. Take a moment, see if you can figure out what you're supposed to do on your own. Hit play when you're ready. Alright, so just like before, we're going to take our given roots and turn them into factors, but before we do that, we're going to realize something. If I tell you that the positive square root of 2 is a solution, that implies that the negative square root of 2 must also be a solution. So when I set up my factors, I shouldn't set up just a factor for x plus 3 and x minus root 2. I also need a third factor, x plus root 2. Now, just like I pointed out on the last problem, we have a conjugate pair. On the last problem, we had x plus 1 and x minus 1. So we went ahead and started with the conjugate pair when we multiplied through because it makes things so much easier. We're going to do the same thing here. Anytime you have a conjugate pair, start with that multiplication. It makes things so much easier. Technically, we could just multiply from left to right, but again, it makes things so much easier if you start with the conjugate pair. I encourage you, once you're done with this problem, hit pause and then try multiplying through just from left to right. You will give up after about 10 seconds because you'll realize it is hideously ugly doing it that way. So we're going to start by multiplying the conjugates. Remember that when we multiply conjugates, it's just a squared minus b squared. In this case, the a value would be x, the b value would be root 2. So when I multiply it through, it's just going to be x squared minus root 2 squared. And remember, when we do root 2 squared, a square root squared cancels itself out. The only thing that would be left would be the 2. Or you can think of it as root 2 squared means root 2 times root 2. Root 2 times root 2 is root 4. Square root of 4 is 2. So quick, easy way to multiply through by a conjugate is just to square the first term, square the last term, and subtract. Difference of squares. Now we can continue to FOIL. X times x squared is x cubed. X times negative 2 is negative 2x. 3 times x squared, 3 times negative 2. Reorder the terms so that they're in descending order, and we have our answer. Now, something I forgot to point out before, but I'm going to go ahead and point out now. Notice the degree of your final answer is third degree. It's a cubic. A cubic should have 3 solutions. We started with 3 solutions. Always double check, not only if you're solving or writing a polynomial, that the number of solutions matches the degree of the polynomial. All right, here's another one for you to try. Hit play when you're ready. So, just like before, we've got a negative root 5. Anytime I have a square root, I've got my conjugate pair theorem that says that I should have another, the opposite root to pair along with it. So if I have negative root 5, I should also have positive square root of 5. So I'll set up my factors just like I normally do. The 1/2 can become x minus 1/2. We have x plus root 5 and x minus root 5. Now, before we jump into it, though, let's take a second look at that x minus 1/2. Man, fractions. I hate fractions. I hate when there's a fraction in my problem. So here's what we can do. We can realize that x minus 1/2 is not the only way to get 1/2 as a solution. Keep in mind, if I have x equals 1/2, instead of just subtracting over to get my factor, there's another way. If I have x equals 1/2, instead of starting with subtracting, let's start by multiplying by 2. In other words, if x equals 1/2, then 2x equals 1, and thus 2x minus 1 equals 0. The factor 2x minus 1 produces a solution of 1/2, just like x minus 1/2 produces a solution of 1/2. It doesn't matter which factor you use. Technically, when you're done, you will have a polynomial that produces these solutions. But wouldn't it be much easier to use this factor as opposed to the one that has a 1/2 in it? I agree. So let's go ahead and replace that x minus 1/2 with 2x minus 1. Now let's multiply through. We will start with the conjugate pair. So if I have x plus root 5 times x minus root 5, I have, once again, a conjugate pair, so I'll just go straight to the difference of squares, x squared minus root 5 squared, which itself is 5, and then I'll finish foiling it out, one piece at a time, and we have our answer. Now let's look at this one. Slightly different, but really it's not. All right, this time I have an imaginary term. Keep in mind, I, again, is the square root of -1. Therefore, the conjugate pair theorem still applies. If 5i is a solution, then negative 5i should also be a solution. So if I set up my factors, I'll have x minus 2, x minus 5i, x plus 5i. So we'll start with the conjugate pair, x minus 5i times x plus 5i. Remember, we still have that same rule, a minus b times a plus b is still a squared minus b squared. So the a value is x, so x squared is just x squared. And then the b value, 5i. Well, 5i squared really means 5 squared I squared, so that would be 25i squared. Now remember, I itself is the square root of -1, so I squared, if I square a root, cancels itself out. I squared is just negative 1. So that means I can replace that I squared with negative 1, multiply it times negative 25, and get positive 25. Now, this is something that's going to happen every time you multiply these complex conjugates. Remember, complex just refers to the imaginary number. Every time we multiply complex conjugates, we're always going to get I squared. Therefore, it's always going to cancel, or it's always going to be replaced with a negative, which cancels with that negative, which makes a positive. Therefore, we can kind of amend our difference of squares rule. When it's difference of squares, real numbers, it's a squared minus b squared. But when they are complex conjugates that we're multiplying through, we're going to end up with that I squared right there. I squared is always negative 1. Therefore, multiplying complex conjugates gives us a squared plus b squared. In other words, a sum of squares. So if they're real numbers, the conjugates multiply through to give you a squared minus b squared, the difference of squares. If they're complex numbers, then the conjugates are going to multiply to give you the sum of squares, a squared plus b squared. So just keep that in mind when you're using these shortcuts. If they're real numbers, it's going to be a squared minus b squared. If they're imaginary or complex numbers, then it's going to be a squared plus b squared. So now I can finish foiling it out. I get x cubed, 25x, negative 2x squared, negative 50, reorder, and I have my answer. Here's another one for you to try. Notice that one of them is just a root and the other one is imaginary. So we can get an opportunity to use both shortcuts at the same time. Hit play when you're ready. Alright, so we'll go ahead and set up our factors. Now keep in mind, if I have 2 root 3 and negative 7i, both of these should have a buddy to hang out with. So I should have negative 2 root 3 and positive 7i to add on there. And I'll go ahead and set up my factors and I'll order them so that the conjugates are right next to each other. Now let's multiply it through. So notice the first pair are real number conjugates, so I'm going to use my difference of squares shortcut formula. So it's just going to be x squared minus 2 root 3 squared. So when I do 2 root 3 squared, it's really 2 squared, which is 4, root 3 squared, which is 3, 4 times 3 is 12. So 2 root 3 squared is just 12. On the other side, though, I have my complex conjugate pair. So when I'm doing a complex conjugate pair, it's going to be the sum of squares. So I'm still going to have x squared, but this time when I look at that 7i, keep in mind the b value is not 7i. I'm not going to read the entire 7i as the b value. The b value is the number in front of the I. So the b value is just 7. Now you could also say the b value is negative 7. It really doesn't matter. We're going to square it anyway. But remember, the b value is the number in front of the I. It does not include the I itself. So the b value is 7. 7 squared is 49. So x squared plus 49. Since it's a complex number, it's a sum of squares. Now we can just continue foiling as normal. X squared times x squared gives me x to the 4th. Then I have 37x squared when I do both the outside and the inside and add it together. When I multiply negative 12 and 49, I get negative 588. Alright, now I think we've got a handle on the others. Let's get crazy. Let's throw in a binomial complex number, 3 plus I. Now let's go ahead and walk through this one together since there is a slight difference to this particular problem. Now technically we could still set this up the same way that we always do. 3 plus I means that 3 minus I is also a solution. I could go ahead and set up my factors. Negative 4 turns into x plus 4. Be careful with the 3 plus I. Keep in mind, if I have x equals 3 plus I, turning this into a factor means I'm going to subtract the 3, subtract the I, so I have x minus 3 minus I. On this one, common mistake occurs, and you're going to write x plus 3 plus I, but really it's just the I that changes sign. It's still a positive 3. I'm still subtracting 3 and then adding I, so it would be x minus 3 plus I. And as before, we can start with the conjugate pair and multiply it through. But here's the part where it's not going to be any fun. So if I assume you are taking notes, I highly suggest that you not write this portion down, because I'm going to go ahead and show you how brutal this problem is doing it the same way we did the other ones, and then I'll show you the shortcut once I go through it. So if I were to multiply through x minus 3 minus I times x minus 3 plus I, I'll just distribute one term at a time. Starting with the x, I'm going to distribute it onto x minus 3 plus I. So I ended up with x squared minus 3x plus ix. Then I'll distribute the negative 3. I get negative 3x plus 9 minus 3i. Then I'll distribute the negative I. Negative ix, positive 3i, negative I squared. Now, we've got a lot of terms here, but notice immediately some of them cancel. For example, the ix's cancel, the 3i's cancel, and for that matter, I squared, remember, I squared is -1, so negative I squared really means +1. We can condense the further terms. Negative 3x and negative 3x gives me negative 6x. 9 and 1 gives me 10. So all of that simplifies down to this. Now here's the thing. When we multiply conjugates, we expect that the roots are going to cancel out. We expect that to happen. But we also expect some other patterns to emerge. Now take a look at this. I have 3 plus I and 3 minus I. If I were to take those numbers and add them together, 3 plus I plus 3 minus I. 3 plus 3 is 6. Positive I and negative I cancel out. 3 plus 3 is 6 though, and notice what number is right here, 6. Also notice where the 10 came from. 10 came from 9 and 1. Well, 9 is just 3 squared. And 1, keep in mind the 1 came from I squared, and the number in front of the I, the b value, is itself 1. 1 squared is 1. And that's where we got the 10. And that's the pattern that's going to emerge. That's going to happen every single time. Now notice what pattern really is there. Let's look at it with just leaving, instead of putting 3 and 1 and numbers in for a and b, let's just leave it as a plus bi. If I take a plus bi and a minus bi and turn them into factors and multiply through, it's going to look just like it did on the last problem. But now I just have a's and b's all over the place. The I terms all cancel out. The I squared turns the negative b squared into a positive b squared. And when I condense the terms, I get this. The ax and the ax combine to give me 2ax, and then I have a squared plus b squared. So again, the linear term has a 2a in front. In other words, if I just take whatever the a value is and double it, or I can say take whatever the a value is and add it to this a value, because of course adding it and doubling it are the same thing, then that's going to give me the number that goes in front of the x. And for that matter, a squared plus b squared, all right, don't you remember that a squared plus b squared is the product of those two complex numbers? A squared plus b squared is really just taking these two complex numbers and multiplying them together. So we have ourselves a handy-dandy little formula. When I have two complex numbers that are in this binomial form, instead of writing my individual linear factors and multiplying it through, let's go straight to the quadratic factor. X squared minus whatever the sum of those complex numbers is, times x, plus whatever the product of those complex numbers is. And the product is always, quick and easy shortcut, a squared plus b squared. So to get the product, it's just a squared plus b squared. To get the sum, it's just either a plus a or 2a, either way you want to do it. So again, when we look at that same problem that we had, this whole mess right here, I never want to see that. That is a complete and utter waste of time. All we need to do is realize that 3 plus I really says 3 plus 1i. If I want to figure out what the quadratic factor is, I can go straight from the two complex solutions here and go straight to the quadratic factor simply by figuring out what the sum is and what the product is. If I take 3 plus 1i and 3 minus 1i and add them together, the i's will always cancel. It's really just 3 plus 3, which is 6, which goes right here. The product, again, is just multiplying them together. And when I multiply them together, that's really just a squared plus b squared. A is 3, so it's 3 squared. Plus the b value is 1, so it's 1 squared. 3 squared plus 1 squared is 10. So that's where I get that number right there. Instead of wasting time multiplying everything through, all you have to do is remember x squared minus the sum times x plus the product. Then we can finish multiplying through, and we get our answer right here. Now why don't you try this one on your own. Hit play when you're ready. So once again, we've got 2 plus 5i, so that tells us 2 minus 5i is a solution. We can go ahead and write out our factors. X equals 0 is going to have a factor of x. But remember, we're not going to waste time writing separate factors for 2 plus 5i and 2 minus 5i. We're going to go straight to the quadratic form of those two factors together. Remember, it's x squared minus the sum times x plus the product. So we'll start with the sum. When I add 2 plus 5i and 2 minus 5i, the 5i's cancel out. 2 plus 2 is 4. Plus the product, remember to get the product, it's just a squared plus b squared. A is 2, b is 5. So 2 squared plus 5 squared, in other words 4 plus 25, gives you 29. So much quicker than actually setting up my linear factors and multiplying it all out, I can go straight to my quadratic factor. X squared minus the sum plus the product works every single time. Distribute the x and I have my answer. One last one. Give this one a try. Hit play when you're ready. Alright, so once again we're going to, if I have 3i and 1 plus 3i, that means I should also have negative 3i and 1 minus 3i as solutions. Again, I don't need to waste time setting up individual factors for each one of these because these complex numbers have shortcuts. Now, the 3i and the negative 3i, recall that when we had problems before, like we had one before, I think it was 7i, it wasn't too bad to just say x minus 3i, x plus 3i, and then FOIL it out. This wasn't too difficult, so I could just really quickly say x squared minus 3i squared, which of course became positive 9. It wasn't too much work to just set up, when it was just 3i by itself, to just set up the conjugate pair, FOIL it out, and get x squared plus 9. Not too bad. But we do have a shortcut now, and you are more than welcome to use that x squared minus the sum plus the product on something as simple as this. Now, do I recommend it? Probably not. It's probably quicker to say, well, if I have 3i and negative 3i, that's going to be x squared plus 9. But I do want to point out that it still works using the more advanced technique. So if I took that 3i and that negative 3i and looked to see what the quadratic factor would be, remember it's just x squared minus the sum x plus the product. The sum of 3i and negative 3i, they cancel out, is 0. So that linear term really is going to cancel out. It doesn't need to be there. Plus the product of 3i and negative 3i, 3 times negative 3 is negative 9, I times I is I squared is negative 1, negative 9 and negative 1 is positive 9. So I get the same answer if I use the x squared minus the sum plus the product shortcut as I would if I just FOILed it out. So either way, it doesn't matter. I would probably suggest just going straight to the binomial x squared plus 9 just by thinking of it as FOILing it out. Now on the other side though, the 1 plus 3i, I suggest using x squared minus the sum plus the product because it's much more cumbersome to multiply through. So if I add 1 plus 3i and 1 minus 3i, I get 2. If I multiply them, remember it's just a squared plus b squared. 1 squared plus 3 squared. 1 plus 9 is 10. So now clean it up and multiply through. X squared times everything gives me that. 9 times everything gives me that. Combine like terms, and I have my final answer. Alright, so we've established how to write a polynomial given roots. Let's turn it back around. Let's come back around to the beginning, and starting with the polynomial, let's find roots. Now again, we've already practiced finding roots before. We've found roots using the GCF method. We found roots using quadratic methods. We've looked at grouping. Now let's look at some more advanced polynomials, some polynomials that don't work with those standard techniques. Now as we progress further in this lesson, you're going to want to make sure that you have a graphing calculator handy. So if you don't have one handy right now, go ahead and pause the video and acquire your graphing calculator, and then hit play once you've acquired it. So what we have here is a third degree polynomial, 5x cubed plus 13x squared plus 4x minus 4, and you're asked to find the remaining roots of the function. I've given you the first root. The first root is 2/5, and I want you to find the remaining roots. Now keep in mind that it's a third degree polynomial, therefore it should have 3 roots. It should have 3 solutions. I've given you one solution. You have to find the remaining 2 solutions. Now we could completely ignore the fact that I've given you one solution and just try to solve this right out, but immediately we're gonna stumble into a problem. There's no GCF that I can pull out. It's not quadratic or of a quadratic form, so I can't use any quadratic techniques. There are 4 terms, so I can attempt grouping, but the problem is 5 to 13, 4 to 4, or 1 to 1. I don't have a common ratio front to back to be able to group this successfully. So the techniques that I currently have will not work on this polynomial. But there is another concept I have, and that's going to require the use of that given root. Imagine I give you the number 50, and I ask you to factor out the number 50. But hold on there. I'll go ahead and tell you 5 is one of my factors. Alright? So if 5 is one of my factors, I can very easily find the second factor simply by dividing. 50 divided by 5 gives us 10. And then 10, a smaller number, much easier to factor, I can realize, well, that's just 5 and 2. So the factorization for 50 would be 5 times 5 times 2. By giving you that first factor of where to start with and dividing it out, I can reduce my 50 down to something smaller, and that's hopefully easier to factor out by hand. So that's the same idea. We're going to start with 2/5, your given factor, that's like the 5 here, and we'll go ahead and divide it out of your given polynomial. That's like dividing 5 out of 50, and then getting a result that we can then factor further. So let's do just that. We're going to divide 2/5 out of this polynomial. Now remember, to divide something out of a polynomial, we're going to use synthetic division. Please make sure you are not still using long division because it's just so much more difficult. Synthetic division, super easy. So remember, the number that goes over here is going to be the root that we're dividing out, and the root that we're dividing out is 2/5, not negative 2/5, it's just 2/5. And then we'll go ahead and list out our coefficients. We don't have any missing terms, so we don't need any zeros. So let's go through this. Drop down the 5. 5 times 2/5 gives us 2. 13 and 2 is 15. 15 times 2/5 gives us 6. Add, we get 10. Multiply, we get 4. And add it together and we get 0. Now let's think about that 0. All right. I told you that this was a root. And if it is a root, it is a factor, it should be able to divide evenly. If you go through your synthetic division and you get anything other than 0 as your remainder, then that tells you that you've made a mistake. So instead of waiting until the end to determine if we have the correct answer, there are points within the problem that we can use as checkpoints to make sure that we're doing this correctly. The fact that I get 0 as a remainder confirms that 2/5 is a root. Thus, I have a happy face. If I don't get 0, then I have a sad face because I know I've done something wrong. But as soon as I get 0, I have a happy face. So let's continue. So again, the 2/5 was a confirmed root already. I've divided out 2/5, and this is what I had left. 5, 15, and 10, or 5x squared plus 15x plus 10. I can now take this remaining polynomial, set it equal to 0, and continue solving. So I'll start by looking for a GCF. I notice that there is a GCF of 5 that I can factor out. And since that GCF was just a constant, it didn't have a variable attached, I can go ahead and ignore that GCF. In other words, divide both sides by 5 and not worry about it anymore. If the GCF is a variable, I have to worry about it. If it's a constant, I can ignore it. So then let's just see if we can factor this further. What are factors of 2 that add to 3? Hopefully you realize that factors of 2 that add to 3 are just 1 and 2, which gives me solutions of -1 and -2. So remember, my original solution was 2/5. I now have 2 more solutions of -1 and -2. The question was not to find all the solutions, it was to find the remaining solutions. So here is my answer. Now, as a side note, just to point out, you might every once in a while get a question that says to write a linear factorization. So in the event that you are asked for a linear factorization is essentially what we were doing in the last bit of problems, where you would start with the solutions and then you would turn those into a product of factors. Linear factorization is just writing out the polynomial in its fully factored form. Well, if these are the solutions, then its fully factored form could look something like this. Remember, -2 comes from this factor, -1 comes from that factor, and 2/5 could either come from x minus 2/5 or 5x minus 2, I think is a bit prettier. So just in case you stumble upon this type of question, this is what it's asking you for. Alright, so here's another one. Why don't you give this one a try? Now, again, I'm going to suggest that you follow strictly the same steps that you did on the last problem. There is a point where you may stumble. If you stumble, feel free to hit play and to catch up to the point at which you are unsure. But trust me, the steps are exactly the same as the last problem. Give it a try, hit play when you're ready. Alright, so we'll start with our given our given root of 3i. We will use synthetic division to divide it out. No missing terms, we'll list out our coefficients. Now at this point we haven't done synthetic division with a complex number involved, but trust me, synthetic division is synthetic division. It doesn't care what type of numbers you're using, just follow the process. We'll start by dropping down the 1. And then whatever I have down here, I multiply it by whatever I have up here. So 1 times 3i is 3i. Then my next step is to simply add it together. Whatever I have here and whatever I have here, I'll add it together. 1 plus 3i. Now here's the point where maybe you had to think about this. Hopefully you didn't think about it too long, because it should be obvious to you. If I'm adding two terms that are not like terms, then I can't combine them. 1 plus 3i is 1 plus 3i. They are not like terms, thus they cannot be combined, so do not try to force them together. So now I have 1 plus 3i, and that gets multiplied by 3i. Now remember, when I'm multiplying 3i and 1 plus 3i, essentially all I'm doing is distributing. 3i times 1 is 3i. 3i times 3i is 9i squared. But of course, I squared itself is negative 1, so positive 9 becomes negative 9. In other words, it's negative 9 plus 3i. Now, I had to do a little bit of scratch work off to the side for that one. At the beginning of this section, I said, make sure you have your calculator handy. You're more than welcome to use that calculator. And this is the situation where you may want to actually just pull out a calculator. Arithmetic is not difficult, all right? But sometimes arithmetic can take a little bit of effort to get it correct. So we're in pre-calculus, not in Algebra 1. We're definitely not in Algebra 1 because we're doing a problem like this. But my point is, if you don't want to waste time doing the arithmetic on some scratch paper, feel free to pull out a calculator and use your calculator to do the arithmetic. So that's what I'm going to do. Let's go ahead and back it up one step, and let's pretend I didn't do this calculation down here. I'm going to go ahead and use my calculator to do 1 plus 3i times 3i. So when I type it in, we got to be careful. When I'm multiplying 1 plus 3i, if I just type in 1 plus 3, well, here's a second. Where's the I button? If you look closely, I have two I buttons. I have one I right here. That's the letter I. I don't want the letter I. I want the number I. The number I is right here. So if I just hit second and the decimal point, I get the number I. So if I just type 1 plus 3i times 3i, notice I get negative 8, when in fact I already know the answer is negative 9 plus 3i. So what did I do wrong? Hopefully you recognize that I am missing my parentheses. The calculator will do exactly what I ask it to do. I am asking the calculator to multiply 3i and 3i, which is negative 9, and then add 1, which is negative 8, when in fact I should have asked it to multiply the entire quantity 1 plus 3i times 3i. That way I get negative 9 plus 3i, which is the answer I expected to go in right here. So again, you can do it by hand, or you are more than welcome to pull out a calculator and just let the calculator do the arithmetic. So let's keep going. Now let's add 9 and negative 9 plus 3i. I don't need a calculator for that. 9 and negative 9 cancel out. We're left with 3i. 3i times 3i, we've already done that calculation. It's negative 9. Add it together, happy face. I got exactly what I expected. I got 0 as my remainder because I already knew 3i was a root. Now I've got this left over. On the last problem, I went ahead and turned that into my quadratic, 1x squared plus 1 plus 3ix plus 3i, and factored it further. But holy jeez, I don't even know how to factor that. Here's where I bring something we talked about a little bit ago into my current problem, the conjugate pair theorem. If 3i is a root, doesn't that also mean that negative 3i is also a root? And if negative 3i is a root, can't I also divide negative 3i out instead of actually factoring this? So let's do that. I've already divided out positive 3i. As our second step, let's divide out negative 3i, since I know it is also a root. We're going to follow the same process, drop down the 1, but you'll find during this second iteration of synthetic division, it always looks a whole lot prettier, and I actually probably don't even need the calculator for the second round. 1 times negative 3i is negative 3i. The 3i's cancel out. I'm left with 1. 1 times negative 3i is still negative 3i. The 3i's once again cancel out, and I have my happy face remainder of 0. So 3i and negative 3i are roots, and my remaining root is going to be found from this guy, x plus 1. 1x plus 1. Set it equal to 0 and solve for my remaining root of negative 1. So my given root was 3i. My remaining roots were negative 3i and negative 1. So that was fun. Let's do it again. Notice this time, though, I've got a slightly more complex number, 1 plus 3i. But just as I said before, the process is exactly the same. As long as you follow the rules of synthetic division, you won't have an issue. If I get to a point where it looks too difficult to multiply in my head, feel free to pull the calculator out and let the calculator do the work. Remember, we need parentheses when we type in the binomials, otherwise you're going to get the wrong answer. So, give it a try, hit play when you're ready. So if 1 plus 3i is a solution, that means 1 minus 3i is a solution. I've got a 4th degree polynomial, which means I have 2 more solutions to find. So I'll start my synthetic division, starting with 1 plus 3i, sprinkle in my coefficients, drop the 1. 1 times 1 plus 3i is 1 plus 3i. Don't need a calculator yet. Negative 3 plus 1 is just negative 2. Negative 2 plus 3i times 1 plus 3i. Here's the point where I could multiply these together and just FOIL it out, or feel free to just pull that calculator back over. So I want to do negative 2 plus 3i times 1 plus 3i. Remember, we need parentheses. Negative 2 plus 3i times 1 plus 3i. So I'm taking that entire binomial, multiplying by that binomial. I get negative 11 minus negative 11 minus 3i. So I'll go ahead and put that in next. Add it with the 6. 6 minus 11 would give me negative 5 minus 3i. Now I'll take negative 5 minus 3i and multiply it. When I multiply this time, I get negative 14 minus 12i, and I happen to know that's not correct, and of course I immediately see my mistake. So here's a good opportunity to catch a problem. That said negative 5 minus 3i, and I wrote negative 5 plus 3i. So that's a quick, easy fix. Let's just hit second enter, and then we'll just go back to the point where I made my mistake. Instead of writing a plus sign, I need that to say a minus sign, so I'll just replace it with a minus and try again. And I get 4 minus 18i, which looks much more familiar to when I did this problem earlier. Add it with the 2, and I get 6 minus 18i. One more step. I'm going to do 6 minus 18i times 1 plus 3i. Let's be a little bit more careful this time. So 6 minus 18i times 1 plus 3i. And I get 60, which is exactly what I was hoping it would be, because now that 60 cancels with the negative 60 and I get my happy face. So I've done my first iteration of synthetic division. Now let's do our second iteration with negative 1 minus 3i. Drop the 1, multiply, and notice 3i's cancel out. We're left with negative 1. Multiply, 3i's cancel out. We're left with negative 6. Again, this second iteration, so much easier than the first iteration. Negative 6, I get negative 6 plus 18i, everything cancels out, I get my second happy face, which is what I expected because I knew both of these were roots. So I have my remaining polynomial of x squared minus x minus 6. Let's go ahead and factor this out. Factors of negative 6 that add to negative 1. That would be negative 3 and positive 2. X equals 3, x equals negative 2, and let's not forget that 1 minus 3i was one of my remaining roots. So, synthetic division can be an incredibly useful tool for helping us solve polynomials where I already know at least one solution. Well, that's all well and good, but what if I don't give you at least one solution? What if I start completely fresh, I give you a random polynomial and say, solve? What do I do then? Well, that's where the rational root theorem comes into play. It's important to remember that the rational root theorem does not itself solve polynomials. The rational root theorem, all it does is that it gives me a possible set of solutions that may or may not be my first solution. Once I find that first solution, I can then use synthetic division to find the remaining solutions, just like we just did. So let's see what the rational root theorem really is. And it really is fancy guess and check. So imagine I give you a polynomial and I ask you what are the solutions. Well, there's an infinite possibility of what those solutions could be. I could just start guessing and checking to see which one's the right answer, but problem is it would probably take me an infinite amount of time to accurately guess and check any random polynomial. So what rational root theorem does is it says, based on what numbers are in the equation, only look at these prime candidates for your solution. So it's fancy guess and check in that we're not randomly guessing. We're only guessing from a certain set of numbers based on the specifications of the problem. So the rational root theorem doesn't give me a solution, it gives me a possible solution. It gives me a list of possible answers that I can then look at each individual possibility and either confirm or deny it as a solution to the polynomial. And for that matter, it only gives me rational solutions. Remember, a rational number is a fraction. The rational root theorem only gives me solutions that can be written as fractions. So if I have a solution of square root of 7, rational root theorem is not going to give me that option. It's not going to give me square root of 7. It's not going to give me 7i. It's not going to give me irrational numbers or complex numbers. It's only going to give me rational numbers. Once I have that list of possible solutions, I can either do it the hard way of using synthetic division, one solution at a time, and looking for the one that gives me a remainder of 0, or we're in pre-calculus now, let's go ahead and cheat and use the graphing calculator to confirm our first root. Once we've confirmed our first root, we can factor out that known root using synthetic division, in other words, what we just did on that last set of problems. And we're going to repeat that process until there's only 2 roots remaining. Once there's only 2 roots remaining, that means our remaining polynomial would be quadratic, and we can solve using quadratic techniques. So let's look at the rational root theorem itself. The rational root theorem says that given a polynomial with integer coefficients, so integer meaning like 1, 2, 3, 4, 0, -1, -2, -3, those are integers. If you have a coefficient of 1/2, for example, you can't do the rational root theorem, but what you can do is multiply the entire polynomial times 2, thereby turning 1/2 into 1, which is now an integer, which you can then apply the rational root theorem to. Let p be the factors of the constant term. In other words, the number all the way at the end that doesn't have a variable on it, that's the constant term. P is the factors of that number. Q are the factors of the leading coefficient. P over Q are all of the possible rational roots of the polynomial. So once we find the factors of P and the factors of Q, we look at all the possible combinations of those factors of P divided by those factors of Q. We write those in a nice neat list, and those become the prime suspects, the best candidates for our solution to the polynomial. Then it's simply a matter of checking each one individually to confirm which one is correct, or cheating and looking at the calculator and then using your list and the calculator in combination to determine which one is your best answer, or which one is your correct answer. So let's look at an example. 3x cubed minus 4x squared plus 8x plus 8. Now remember, you should always start by attempting some easier techniques. Look to see if there's a GCF you can pull out. Look to see if it's in a quadratic format. Look to see if you can group. If I look at these, 3 to 4, 8 to 8, I can't group this one. Grouping is off the table. So is GCF, so is quadratic. The only option we have is the rational root theorem. So I'll start by listing out my factors of P and Q. P, again, is the factors of the constant term. Factors of 8 would be 1, 2, 4, and 8, but also -1, -2, -4, and -8. So when I list out my factors, always make sure you put positives and negatives in there. Q is the leading coefficient, in this case 3. Factors of 3 would be positive -1, positive -3. But I don't want factors of P, I don't want factors of Q, I want factors of P over Q. So what I'm going to do is I'm just going to list out my factors one at a time. I'm going to take all my factors of P and divide by my first Q. If I take 1 over 1, 2 over 1, 4 over 1, and 8 over 1, I have 4 possible P over Qs. Then if I take all those same factors of P and divide it by my next Q, 1 over 3, 2 over 3, 4 over 3, 8 over 3, by doing it methodically like this, I can be sure that I have every possible combination of P over Q. So what I have here are not 8 possibilities. I technically have 16 possibilities as to my first solution for this polynomial. Now remember, these are only the possible rational solutions. There could be solutions that have square roots in them. There could be solutions that have imaginary numbers. But these are going to be if there is a rational root, it's somewhere in this haystack. So in Algebra 2, you were told to pick one of these numbers at random, apply synthetic division, and hope that the remainder is 0. We've got 16 numbers here, so you theoretically could have done synthetic division 16 times before you realized that you made a mistake on the second one, and it was actually the second one that you picked. We're not going to waste our time with that in pre-calculus. We're going to go ahead and pull that calculator back out, and we're just going to go ahead and use the calculator as a tool to assist in our analysis. Now, I could simply, synthetic division looks for the remainder. The remainder is the same thing as the value of the function. I could, just like I did with synthetic division, pick a number at random, plug it into the function, and look for which one equals 0. But again, this is a graphing calculator. Another name for a 0 is an x-intercept. So let's go ahead and graph that function, see where it crosses the x-axis, and then estimate based on the values of p over q what that value actually is. So let's just type it in. 3x cubed, to get the cube, we'll hit the caret key right there, minus 4x squared plus 8x plus 8. And we'll go ahead and graph it. Now, if you are not seeing what I am currently seeing, it's probably because you still have your window adjusted for a problem that you did previously. So what I always suggest when you're starting a problem, hit zoom 6 or zoom standard to make sure that you are seeing the standard viewing window, and then you can adjust it from there. Now notice I see it crossing somewhere between -1 and 0. I can't be sure just by looking at it, but I know it's definitely crossing somewhere between -1 and 0. Now it's a cubic. I expect it to have at most 3 x-intercepts. Now it's possible that the other 2 x-intercepts are simply outside my viewing window. Or it's possible that the other 2 x-intercepts are actually not x-intercepts. Maybe they're imaginary and thus don't actually cross the x-axis. But it really doesn't matter. All I need is one solution to get started. And that first solution, again, is somewhere between -1 and 0. So let's take a second look at our possible roots. I have 16 roots here, but only 2 of them are between -1 and 0. And that's going to be -1/3 and -2/3. So out of these 16 possibilities, only -1/3 and -2/3 are really an option. So if I look a little closer, it does look like it's a little bit closer to -1 than it is to 0. So I'm really pretty sure at this point that -2/3 is my solution. But I'm not confident until I confirm it. And I can confirm it simply by taking -2/3 and plugging it into the function. Easy way to do that is to use the trace feature. Tracing is like evaluating at an x value. I want to evaluate at -2/3. Oops. I want to evaluate at -2/3. I'm going to hit enter to see what the y value is. And the y value happens to be 0, which confirms that -2/3 is an x-intercept. So since -2/3 is in fact an x-intercept, I can say that -2/3 is my solution. -2/3 is my first solution. I have a given solution now, -2/3. Let's find the remaining roots using the exact same technique I did in the last set of problems by using synthetic division. So I will divide out -2/3. Following the same process I did before. I already knew -2/3 was going to work, so I better get my happy face. If I don't, I know I made a mistake. I have my remaining polynomial, 3x squared minus 6x plus 12. Common factor of 3, let's go ahead and divide it out. And then I'll look for factors of 4 that add to -2. I'll think about it, think about it, think about it. There are no factors of 4 that add to -2, therefore I must have to use the quadratic formula. Opposite of b, plus or minus the square root of b squared, minus 4ac, all over 2a. Let's clean that up. I'll start on the inside. 4 times 4 is 16. 4 minus 16 is -12. Anytime I have a negative, let's go ahead and pull that out as an I. Now, on the test, if this is a free response question, feel free to stop right here. You do not have to go any further than this. You do need to at least pull the I out. Anytime you have a negative, don't leave it as a negative. Pull out the I. But you don't have to simplify the radical any further. Now, if it's a multiple choice, keep in mind that the multiple choice answers will be fully simplified. Thus, you need to be prepared on how to simplify the radical. Root 12 is the same thing as root 4 times root 3. So let's just pull out the root 4, which itself is 2. So I have 2 on the outside, root 3 left on the inside. So I have 2 plus or minus 2i root 3. And wait a second, we notice I have 2's on the top, 2 on the bottom. In other words, I have a GCF of 2 that can be factored out on the top, and then that 2 can cancel with the 2 on the bottom, leaving 1 plus or minus I root 3. Please don't make that common mistake of saying 2 divided by 2 cancels out, and you're just left with I root 3. 2 divided by 2, yes, it does cancel, but it doesn't leave nothing. It leaves a 1. 2 divided by 2 is 1, not 0. Don't just leave plus or minus I root 3. It's 1 plus or minus I root 3. And of course, don't do that other common mistake of forgetting that didn't we already find a solution at the very beginning? Negative 2/3 is a solution. It needs to be listed along with 1 plus I root 3 and 1 minus I root 3. I have 1, 2, 3 solutions for my original cubic polynomial, so I know I have enough solutions. I hopefully am correct. Alright, here's another one for you. Hit play when you're ready. Alright, let's go ahead and follow the same path we did before. I can look to see if it's factorable, but even by grouping I don't have common ratios, so I can't factor it. We'll list out our factors of p, which are 1 and 5, positive, negative, 1 and 5. Factors of q would be positive, negative, 1 and 2. P over q would be 1 over 1, 5 over 1, 1 over 2, 5 over 2. So from here I can either guess and check to see which one is correct, or I can just pull out the calculator and do it that way. So I have 2x cubed minus 5x squared plus 12x minus 5. Let's go ahead and graph it. I see a solution somewhere between 0 and 1, so let's look at our list. There's only one option between 0 and 1, and that's going to be 1/2. So we have our first solution. Let's use synthetic division to find our remaining solutions. So the 1/2 divides out evenly, which I expected it to do so. We can go ahead and divide out the 2 to get rid of the common factor. We need factors of 5 that add to negative 2. Once again, you're not going to find one, so let's just jump to the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. On the inside there, we have 4 minus 20, which is negative 16. And this time, instead of just pulling out the negative and reducing, I know what the square root of 16 is. It's 4. So the square root of negative 16 would be 4i. Once again, I have a common factor between the top and the bottom, so we can go ahead and reduce. 2 divided by 2 is 1. 4 divided by 2 is 2. So I have my answer of 1 plus 2i, and of course, let's not forget about 1/2. Alright, here's one more problem for you. Hit play when you're ready. Alright, so notice this time we have a 4th degree polynomial. When we go through and find our first solution and divide it out, I'm going to be left with a 3rd degree polynomial. So in other words, we may have to do the rational root theorem more than once to get down to our 2nd degree polynomial that we can then solve using quadratic techniques. So be prepared for that. If no matter what degree you're starting with, you may have to repeat that rational root theorem over and over again until you get down to the 2nd degree polynomial that you can then solve using quadratic techniques. We'll go ahead and list out our p's and q's. The p's would be 1, 3, and 9. The q's, notice the leading coefficient is 1, meaning there's only one value for q, positive, negative 1. So if I take 1, 3, and 9 and divide by 1, I'm just going to have 1, 3, and 9. So in other words, this one where you're going to have to repeat the process, I decided to be a nice guy to you and give you a q value of 1. That always makes things super easy. So now we're going to go ahead and check the calculator to see what this graph looks like. We're going to start with x to the 4th plus 6x cubed plus 10x squared plus 6x plus 9. Alright, so it's a 4th degree polynomial. We're going to talk about in the next lesson what a 4th degree polynomial graph should look like. And it's going to typically look like a W. Now you can kind of see the W here. Here's one hump and here's the second hump. The fact that this second hump doesn't pass the x-axis means 2 of our solutions are going to be imaginary. But we have a solution right here. If you look closely, it's hitting the graph at what looks like negative 3. Which is, in fact, one of our possible solutions. So if I trace negative 3 just to be sure, I have confirmed that negative 3 is a solution. Negative 3, 0. So let's go ahead and take negative 3 and divide it out of our polynomial. Drop the 1. 1 times negative 3, blah, 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 and I get my happy face at the end. So negative 3 is the solution, and here is my remaining polynomial. Now, what I could do at this point is basically start over. This time my p-value is 3, so my only possible factors would be 1 and 3. My q-value is still 1, so I still have p over q's of positive negative 1, positive negative 3. And I could repeat the process. Or I can realize something. 1 to 3, 1 to 3. We now have 4 terms that have a common ratio in the front and in the back. I don't have to continue with rational root theorem if I don't want to. If I see an easier technique, you are more than welcome to jump to that easier technique. In this case, grouping is an easier technique than the rational root theorem. So that's what I'm going to do. I'm going to group the first 2 and the last 2. I'll factor out x squared out of the first 2. On the last 2, there's nothing I can factor out, but I have to factor out something. So I'm going to factor out a positive 1, just to show that I did technically factor something out. So x plus 3 is going to be the common factor between the two of them. So I have x plus 3 and x squared plus 1. Set each factor equal to 0. I'm going to get negative 3 for this guy. And on x squared plus 1, that's going to produce positive negative I, which is what I expected, remember, when I got that hump that didn't cross the x-axis. I expected some imaginary solutions. So I have solutions of negative 3 and positive negative I, but of course I also have that fourth solution of negative 3. But notice negative 3 is already listed down here. I don't need to list it twice, but it is helpful to recognize a multiplicity of 2. So here is my final answer, negative 3 and plus or minus I. Now, next time we're going to start talking about graphing. And when we're graphing polynomial functions, the main technique that we use is going to be finding intercepts, finding x-intercepts and y-intercepts. We're also going to couple that with the concept of multiplicity. A second ago I mentioned that the negative 3 had a multiplicity of 2. Notice that the graph at negative 3, it didn't cross the graph, it touched negative 3 and bounced back. It didn't cross the x-axis, it bounced off the x-axis. And negative 3 had a multiplicity of 2. Keep that concept in mind as we jump into the next section.